Among the small and medium-sized cycloalkanes, cyclohexane is the most stable of the series because it's completely strain-free. It's got CH and CC bonds that are perfectly staggered at 60-degree adjacent dihedral angles, and it's got essentially no angle strain with perfect tetrahedral bond angles between the CC and CH bonds. So cyclohexane is essentially strain-free. This makes it extremely common both in stable organic compounds and in transition states where new bonds are forming and breaking. When that happens in a cyclic manner, a six-membered ring is quite frequently involved, and that six-membered ring often has the chair conformation. So in this video, we're going to learn how to draw the chair conformation and get an overall picture of the conformational situation for cyclohexane, which includes conformations other than the chair that are higher in energy. We're going to explore these conformations because they're on the pathway from one chair to the so-called flipped chair form, where the head becomes the feet and the feet become the head, if you like, of the chair and the chair flip process. And so some appreciation of these conformations is going to be important. There are also broader lessons about strain that we can take away by analyzing these conformations as well. But to begin, I wanted to take a look at a three-dimensional model of cyclohexane and note a couple of things about the 3D model of this compound. One is, if we look down on it like this, it does have the appearance of a flat hexagon, and quite frequently in skeletal structures, cyclohexane is just represented with a flat hexagon. We can use things like wedges and dashes to represent bonds coming out of the screen or going back into the screen, for example, on that flat hexagon, and it's a reasonable approximation of the geometry of cyclohexane. But if we look at an actual 3D model and we look at the molecule sort of from the side or rotate the model like so, we see that that molecule is definitely not planar. There's an inherent zigzag to the cyclohexane ring that gives it this chair shape in its lowest energy conformer, with the head of the chair on one side and the feet on the other. Another thing to notice concerns the hydrogens. The hydrogens here have two sort of qualitatively different orientations. Half of the hydrogens are aligned roughly perpendicular to the ring. If we imagine kind of an average plane formed by the 6 carbons of the cyclohexane ring, there are hydrogens that are sticking straight up or straight down above or below that plane, almost perpendicular to it. These are what we call the axial hydrogens. The 6 other hydrogens look almost parallel to that sort of pseudo-plane. They're parallel to carbon-carbon bonds within the ring. And these are what we call equatorial, because they're roughly speaking in the sort of equatorial region of the molecule, if we think of that sort of average plane of the carbons as the equatorial region of the molecule. The way we draw these and the way we think about them is very, very different. These are very, very different positions within the cyclohexane ring. And so careful appreciation of axial versus equatorial substituents and learning to draw them properly is really, really important as we're thinking both about cyclohexane itself and substituted cyclohexanes, where we start replacing those axial and equatorial hydrogens with other groups. So, before we get into the details of drawing chairs and their substituents, though, I wanted to get an idea of the overall conformational picture for cyclohexane, looking at some of the other important conformations. And the first one I want to look at is the boat conformation. The boat looks like a chair where we flip up the feet to create a second head, and now the overall molecule looks like a boat, right? This is a local energy maximum on the conformational coordinate or conformational energy diagram for cyclohexane going from one chair form to another. And it's an energy maximum because of the severe eclipsing that shows up in this structure. With all of these CH eclipsing interactions and some carbon-carbon bond eclipsing interactions as well, that's pretty bad torsional strain going on in the boat conformation. There's also a steric interaction between the two H's that are in a 1-4 relationship at the kind of bow and stern, if you like, of the boat. And this is known as a flagpole interaction because these CH bonds, if we think of the boat conformation as a boat, look like flagpoles at the front and back of the boat. And those H's are bumping into each other pretty badly. This is a source of destabilization, and it's a steric strain since it's the CH bonds, electron clouds taking up space. That's the essence of the destabilization here. Now, being a local energy maximum, this is going to adjust itself somehow to get down to a lower energy structure. And what happens from the boat is a puckering or a twisting of the front and back bonds to create what's called the twist boat structure. So there's some torsion that goes on here at the indicated bonds, and we end up at the twist boat. And the twist boat is not as stable as the chair form, but is an energy minimum. Nonetheless, it's a local energy minimum. Local energy minimum. So not as low in energy as the chair form itself, but it's on the way to the chair form. There's one more barrier for the twist boat to get over. That's known as the half chair. And once we surmount that half chair, we are at the other chair form of cyclohexane. This slide makes a very important point about chair cyclohexane. Any cyclohexane, even the parent cyclohexane with no substituents, has two distinct chair forms. For cyclohexane itself, we can think of one as kind of a right-leaning chair and the other as a left-leaning chair. And these two structures interconvert via a series of bond rotations known as the chair flip. And there are multiple energy minima and maxima along the pathway from one chair to another. So this is nothing more than a conformational energy diagram like we've seen for ethane, propane, and butane so far. It's just a lot more complicated because we've got a ring that's undergoing a lot of conformational changes and a lot of energy maxima and minima along the way. To give you a sense of the energetics going on here, though, I do want to point out that the barrier here to rotation is much higher than any sort of conformational rotation barrier we've seen so far. 45 kilojoules per mole is way, way higher than, for example, the energy barrier associated with rotation in butane that converts a gauche conformer into the anti-conformer, for instance. And if you do the math on rate constant and half-life, the half-life here is about 10 microseconds. And this is much, much, much slower than the bond rotations in acyclic alkanes that we've seen so far. And again, the basic reason is because multiple bonds are having to rotate at the same time to cause this flip from one chair to another. So the first thing that happens is a flipping up of the feet to what's known as the half chair structure. The half chair structure has terrible eclipsing because all but one of the carbons are in a common plane. All of these carbons are coplanar. So twisting continues to alleviate that really bad torsional strain, and that gets us to the twist boat. Now, to continue on to the next chair, the twist boat rotates a little bit more to create the boat structure. And we saw previously this is a local energy maximum because of those flagpole interactions and pretty bad eclipsing. The eclipsing is not as bad as in the half chair, but it's still pretty bad. And so this can rotate into the other enantiomeric or mirror image twist boat of the one on the left. And that gets us to here. Finally, our former head of the original chair rotates down into the plane of all of these carbons to create a new half chair. And then finally, that flat part of the half chair rotates down to create the other chair form. So a bit of a mouthful to work through all these conformational changes. One thing that I highly, highly recommend, and I'm going to post a video for y'all in Chem 2311 that illustrates this very quickly, that you can just put on a loop to really, really get in the head of the cyclohexane chair flip. I encourage you to watch a video of the overall process. It'll give you a sense of how bonds rotate and the intermediates and transition states involved in this conformational change. There's kind of a lot going on, though. At the end of the day, you'll notice it looks very much like taking a lounge chair and flipping the feet up to the head and flipping the head down to the feet. There is another important thing that happens here, though. associated with the CH bonds, or the substituents of the cyclohexane ring. And we can see that if we look at what's going on in this diagram right here. Let's focus in on a couple of the red hydrogens. Notice that this red hydrogen starts in an axial position, roughly perpendicular to the average plane of the ring. But after the chair flip, well, this carbon has flipped down and has become this carbon right here. And in so doing, that axial H has flipped into an equatorial position. The chair flip interconverts axial and equatorial groups attached to the cyclohexane ring. And this interconversion can change the energy of the molecule for substituted cyclohexanes. Now, as we see on this slide, for cyclohexane itself, because all of the substituents, quote unquote, are hydrogens, there's no change in energy, right? These structures are perfectly superimposable, right? They are pretty much identical energetically speaking, but when this is not an H, but a substituent, an R group, now all of a sudden we can actually think of these two chair forms as diastereomers, and that means they're going to have different energies. Now that we've seen the overall conformational picture for cyclohexane, we're going to take a step back and learn how to draw chair cyclohexane. This is something that you'll definitely want to get familiar with, again, because of the ubiquity of six-membered rings in organic chemistry. You'll see them again and again and again and again in structures. There are many different ways to draw chair cyclohexane, but I'm going to show you the approach that I was taught first and that I still use to this day to draw cyclohexane, and then I'll show you an approach recommended by Klein in his textbook that's going to get to the same result just via a bit of a different method. The method I like to use, I call the parallel lines approach. And it takes advantage of this idea that if we look at chair cyclohexane, there are parallel lines that are built into the structure. This carbon-carbon bond is parallel to this carbon-carbon bond. And this bond is parallel to this bond. And this bond is parallel to this bond. And so, provided you start with a slanting line and draw kind of a wide V shape for the second line, you can use this parallel lines idea to draw all 6 carbon-carbon bonds of cyclohexane relatively easily. So the way I go about it is I start with one of those kind of almost vertical bonds, and I like drawing my chairs in sort of a left-leaning way like this. I think a lot depends on your dominant hand and that kind of thing, who knows. But in any event, I start with this, and then I draw another parallel line, and what I'm actually going to do in Notability is just copy and paste to make my life a little bit easier here. Second parallel line lined up with the first. These are going to be our sort of outside bonds of the cyclohexane chair, carbon-carbon bonds. And then we're going to draw the next pair of bonds as kind of a wide V shape. And Klein mentions this in his process as well. So notice that we're going to draw kind of a tilted V, something like this. And then the next line is parallel to this at the other upper carbon of the other line that we drew sort of second. So the next line is going to go here. And again, notice these two lines are parallel to each other, parallel lines again. At this point, the clever will notice we've implied 6 carbons. This looks like 2 propane molecules, right? And so all we need to do now, as Klein describes it, is connect the dots. Connect the carbons that are close to each other that we haven't yet bonded to each other. And because of the magic of geometry, with the first 2 sets of lines parallel to each other, these lines will also necessarily be parallel to each other. So there it is. This is chair cyclohexane, at least the carbon-carbon bonds. We're not going to worry about the substituents just yet. That's coming very soon on a future slide. The process Klein recommends is going to get us to the same result, just via a different sequence of steps. He recommends drawing the sort of wide V first, and then drawing the sort of parallel other side, drawing a line like so, and then finally connecting the dots. So really the only difference, as far as I can tell, is whether you start with the parallel lines or you do the V first and then draw sort of a parallel V and then finally connect the dots. And connecting the dots is always the last step, because you'll always end up with sort of 2 propanes oriented the right way, and you're just going to connect the ends of those propanes together to create the 6-membered ring. Now let's start thinking about the substituents. Each carbon in cyclohexane has one substituent roughly perpendicular to the plane of the ring, that's the axial substituent, and one group that is roughly parallel to the plane of the ring, and that's what we call the equatorial substituent, or the equatorial hydrogen. Now, the axial hydrogens are always going to be sort of straight up and down if you draw the chair as we've described it so far, if you draw the carbon backbone of the chair as we've described it. The axial bonds will alternate at adjacent carbons, going up, down, up, and down. The equatorial hydrogens or substituents are a bit more difficult to get a handle on, though, because these will also alternate up, down, but they'll be roughly in the plane of the ring. And the thing we should notice about this is that the equatorial bonds are parallel to the carbon-carbon bonds in the ring 2 bonds away. So let me carefully show you what I mean by this. This Y group is equatorial, and this carbon-Y bond is parallel to the carbon-carbon bond in the ring that is 2 bonds away from this carbon connected to Y. So here's 1 bond, here's 2 bonds. And notice this bond at position 2 is parallel to the carbon Y bond. Say we had another equatorial substituent on the other side of the molecule. It would be aligned this way, with its alignment parallel to the bond here and to the bond here. And notice those two are parallel to each other based on the way we drew the carbon backbone of cyclohexane. And so the equatorial Y substituent here will be parallel to both of these bonds. All right, now what we're going to do is fill in all the axial and equatorial substituents. And I'm actually going to do it with both a right-leaning and a left-leaning chair. So we can get a sense of what the chair flip does to the axial and equatorial groups. So let's start with the sort of right-leaning chair on the left-hand side here. And I'm going to start with the axial substituents because these go straight up and down pretty straightforwardly. There's not too much geometry to worry about here. The one thing you do want to worry about is to make sure that you're representing tetrahedral carbon the right way. And to do that, look for a point formed by the carbon-carbon bonds at each carbon. The axial group is in the same direction as that point. So here, for example, the axial group of this carbon is pointed straight up because the 2 carbon-carbon bonds there point up like so. Once you've got that down, you just go around the ring alternating up, down, up, down, up, down. So up, down, up, down, up, and down. And occasionally, depending on how you draw the chair, this might end up kind of behind the carbon-carbon bond in the ring. So you may see a bit of a broken bond here if that ends up in the back. Although here, we've done a nice job of drawing the chair so that we've got enough space to show that axial group in the back without worrying about this bond kind of getting in the way. All right, so these are the axial groups, and I'm going to label them with a little a in this conformer to show that they are axial in this conformer. And I'm also going to give them some red highlighting because when we draw the other chair, we're going to see that these go from axial to equatorial orientations. All right, now the equatorial substituents. This is where we got to be really, really careful. The equatorial substituents are parallel to the carbon-carbon bonds in the ring 2 bonds away from our carbon of interest. So here, for example, if this is our carbon of interest, I'm looking at this bond as my reference for how to draw the equatorial group at that position. So it's going to be parallel to that bond, roughly speaking, here. When I go to the next carbon, so say I'm looking here, I'm counting 2 bonds away. My point of reference is this bond. And of course, it doesn't matter which direction you go, right? I could use this bond as my point of reference or this bond. Those are parallel to each other, so I'm going to get the same orientation regardless of where I'm looking, and that's going to be essentially here for the next equatorial position. The next equatorial position, well, now I'm here, and I'm looking 1, 2 at this bond here. This bond here is my point of reference. Could also look here and I get the exact same result. So the equatorial group here is parallel to those bonds, and that is right about there. Now at the next carbon here, if I'm looking at this carbon, now these are my bonds of reference. And so the equatorial group there is right about there. Next carbon, now I'm looking here. I look 2 bonds away. That's going to be either there or there. And in both cases, I'm led to an equatorial group like so. And then finally, last but not least, this carbon that's kind of in the back, I'm looking here and here for my point of reference. And now that equatorial group is aligned this way. And notice also that this equatorial bond is parallel to this equatorial bond across the ring. Same thing's happening here. This equatorial bond is parallel to this equatorial bond. And for a third pair, there and there, these 2 equatorial bonds are parallel to each other. So now let's label these as E, E for equatorial. I'm going to give them blue highlighting in this particular conformer as well. And before we dig into drawing the other conformer, what I want you to think about is what's going to happen when we flip the chair. I'm going to number the carbons to make it as clear as I possibly can what happens when we flip this chair. The head becomes the feet, and the feet become the head. So carbon 4 is now here. Carbon 5 is here. 6 and 1 and 2 and 3 in the chair flipped form. And let's again lay down the axial groups pretty quickly. Up, down, up, down, up, down. Looking for an upward pointing pair of CC bonds to start our drawing. So it's going to be right about there. And then we're just going to alternate. Up, down, up, down, up, and down. And actually here, this chair is a bit more compact. So I'm going to show an example of an axial bond that is sort of cut off by this ring CC bond in the front. These are the axial groups. But notice that this upward pointing group at carbon 4 is the group we labeled E previously. It's the blue group. If we think about where the equatorial group is at that carbon, the equatorial position is here. And what the chair flip has done has flipped this E group up into an axial position in the chair flipped form, in the other conformer. And what was the axial kind of down position is now flipped up into an equatorial position. This is what happens upon a chair flip. Now, for the others pretty quickly here, I'm just going to add them parallel to the bonds, 2 bonds away, as we've done, as we saw in excruciating detail for the first chair form. And I think I got them all. 1, 2, 3, 4, 5, 6. Yep, got them all. And here again, notice that all of these were axial in the original conformer before the flip. After the flip, these are now all equatorial. And again, it's worth watching a video of the cyclohexane chair flip enough times until you've convinced yourself that this is true. Axial groups become equatorial, and equatorial groups become axial. And as just to note a point that we'll make again later in more detail, this doesn't change what's up and down. If we're thinking about wedges and dashes in that flat hexagon structure for cyclohexane, the up and down groups are still the same. For example, the blue group at carbon 4 would be considered up. If we think about looking down on the molecule like this, both in this chair conformer and in this chair conformer, where it's more obvious that that group is up, but nonetheless, it's still, from a stereochemical point of view, in the same place. So the blue groups are now axial in the other chair form. 6 axial blue groups, and the red groups now are equatorial, and there are 6 of those. And this is what the chair flip does. It converts the axial groups into equatorial groups and vice versa, and changes the head of the chair into the feet of the chair and vice versa.